Okay, I'm gonna look at that problem that I spoke about last class. It's the inverting amplifier with multiple resistors in the feedback path. It's this one. So we have an inverting amplifier, inputs going into the inverting terminal. We have multiple resistors in the feedback path right there. And we are asked to determine an expression for the gain of this amplifier configuration. Okay, determine AV. Now, we know AV is the ratio of V out, the output voltage, to V in, the input voltage, right? So we know we need to find equations that contain both V out and V in. All right, let's take a look at what is given to us. First thing we look for is whether negative feedback is present or not. The answer is yes, negative feedback is present. Output is being fed back into the inverting input, so negative feedback. Thus, we can assume that Vi, the difference between the two terminals, is equal to 0. Secondly, we have the non-inverting input connected to ground. Because that's connected to ground, from virtual short concept, we can say that the inverting terminal is also connected to ground. Okay. So as usual, we'll assume that Vi and II are equal to 0 because of the virtual short and virtual ground concept. So now we need to generate equations where we have V out and V in. Okay. So standard techniques, we only have 3 techniques: Ohm's law, KVL, KCL. Right. So we'll apply all of them in any order we want to generate our equations. So first up is node number 1. And here's node number 2. Here's node number 3. 1 is at the input, 3 is at the output, and node number 2 is right here, this connection of resistors. Okay. So if I apply KCL at the inverting terminal right here, I obtain I1, I2, and II. II is already 0, so nothing is going down this pathway. Everything is going up here. And so I can straight away write I1 is equal to I2. Okay. And that would be a safe assumption for any kind of non-inverting circuit. If the non-inverting terminal is grounded, then we can automatically assume for our analysis that there is no voltage and no current going into the input. So Vi and II are 0. Okay, that's what this is. Then let's apply KCL at node 2. Okay, node 2 is here. Now, on the input side, we have I1 and I2, meaning we'll somehow represent V in our equation for I1. Okay. And then, of course, we'll write an equation at node 3, and we will incorporate VO, the output voltage, in that equation. So now we want to apply KCL at node 2. Well, at node 2, these current directions are already given to us. I3 is shown as going up, I2 is shown as coming up, and I4 is shown as leaving the node. So we have I2 and I3 combining to give us I4. So I2 plus I3 is equal to I4. Each of those currents can be described in terms of the resistor voltages. So I1 can be described as the voltage across R1, VR1 divided by R1. I2 can be described as VR2 divided by R2. And same thing for I3 and for I4. Okay. So I1 is VR1 over R1. I2 is VR2 over R2. And I3 is VR3 over I3. Now, again, our goal is to somehow get V in into these equations. So we can describe VR1, the voltage across the resistor R1, as the difference between the two node voltages. So VR1 can be described as V in minus V minus. V minus is already 0 from our assumption at the beginning. And so I can simply write I1 is V in over R1. Does everyone see that? Let's take a pause. Let me know if you have any questions thus far. All good? All right, so we somehow managed to get V in one of our equations, right? That was the goal. Now let's look at the others. I2 and I3 are at this node, okay? Now that node, we have R3 that is connected to ground. If that is physically connected to ground, and the non-inverting terminal is also physically connected to ground, as is this node and as is this node, let's simplify it by drawing a line right there. Okay, let's go all the way here. So all of this is connected together physically. And then this, of course, is also ground. So this point is the exact same as these 3 points. Okay, it's all connected to ground. It also means that this point is connected to this point right there, the inverting terminal, because of the virtual ground concept. And so I can redraw this section right here. R2 and R3 is physically connected to ground here, and this is virtually connected to ground, which is this end of R2, like this. Does everyone see that? Virtual ground. So we can create a loop like this for R2 and R3. And what that does is, for the purposes of analysis, I can state R3 and R2 would be in parallel because they are connected at one terminal right here physically, and the other terminal, we can say they're connected virtually. And again, this is just, again, it's a concept. We use it for the purposes of analysis. And this is actually how the circuit actually functions. Okay. So you have a virtual connection here, you have a physical connection here. That puts R2 in parallel with R3. If R2 is in parallel with R3, that means the voltage across the two, the voltages, the respective voltages are also the same. So I can say VR3 is the same as VR2. And if it's the same loop, then this current and this current must have the same magnitude. They must have the same magnitude. And so I can say I3 is equal to VR3 over R3. And VR3 is the same as VR2. So it's VR2 over I3. Well, VR2 in terms of Ohm's law can be written as I2 times R2. And so I3 goes from this to this to this. I3 is now expressed in terms of I2. Now, the question that might come up is, why are we doing all of this? And the answer goes back to, we want V in and V out in those equations. So if you're starting at any node, we want to go either towards V in or we want to go towards V out. We want to somehow have V in our equation and have V out in our equation, right? The goal is to determine V out or V in. So we need both those quantities. So here the resistors are in the feedback path. So the objective is to somehow get V in into that equation. So if we go from I3 and finally substitute I1 into that equation, because I1 is equal to I2. And we established that at the beginning. I1 is equal to I2, right? So again, we are going from I3, VR3, VR2, VR2, we introduce I2 in there. And from there, last substitution would be I1. And once we have I1, we already determined I1 was V in over R1. Okay. And so we plug that in and we obtain an expression for I3, which has V in. We are slowly and steadily moving towards the output. Yes. Yes. So I3 and I2 would turn out to be the same in this case. But that's just, I'm talking about just these two resistors. Okay. If we talk about this circuit right here, then it's obviously not the same. Then it's I2 plus I3 is equal to I4. So technically for this problem, it should not be, wouldn't be the same. But I was just talking about this circuit right there. Both are parallel, have the same voltage across it. And if it's the same resistance value, then they would be the same current. Okay, so here we started with I1, then we went to I2, now we are up to I3. And we want to move towards the output, which is I4. And so if you go to the output loop, we can plug in the values for I3, I2, and I1 into this equation right here. I4 is the sum of I2 and I3. So we can plug in I2, we can plug in I3, and obtain an expression for I4. So V in times 1 over R1 plus R2 over R1 times R3. So you almost reached the output now. Now all that's left is to somehow write equations where we somehow can get V out into those equations. So we do the same technique, we apply the same technique, and we write out a expression for the output loop. In the output loop, we have R3, R4, and R2, sorry, RL. You write a KVL around that loop. Sum of all three voltages must add up to 0 because for any electrical loop, they should sum up to 0. Take V out on the other side, rearrange the terms, and I can get V out is minus I3 R3 plus I4 times R4. All that's left is to plug in the equations we found above for I3 and I4 and rearrange the terms to obtain V out and V in on one side. And when we do that, you obtain this expression right there. And that is the gain expression for this inverting amplifier. Okay, that is the gain expression for this inverting amplifier. So I'll do a brief recap and then we'll take a pause. Okay, what we did was we started on the input side. We applied KCL here. The assumptions, the usual assumptions are made. And so we can say I1 is equal to I2. We applied KCL here to get our first equation. Then we rearranged the terms, applied Ohm's law to obtain V in these equations. Then we slowly moved towards the output. So then we applied KCL here. Once we applied KCL there, we substituted this into this resistor, and then this right there in R3. So we now have V in into this equation. And from here, we again move towards the right, towards the output. So now in the output side, we have VO. Once we move from left to right, we now have V in here, and we have VO over here. We rearrange the terms for VO and V in, and we obtain an expression for the gain of the circuit. Okay, so let's take a pause, think over the approach, and let me know if you have any questions. The steps make sense. Okay. So if I was to give you a circuit with like 10 resistors in the feedback path, you'd be able to solve it. The answer is yes, you would be able to solve it. Only requires multiple steps and taking track of all the voltages and the currents, but the approach would still be the same. Here's the result. So as an example, let's say all resistors, all four resistors that you see here, R1, R2, R3, R4, are all the same, 1 kilo ohm. Okay. If that's the case, and we calculate the gain, we end up with -3. Okay, so gain of -3. If all four resistors, R1, R2, R3, R4, are all the same value as 1 kilo ohm, or any value, doesn't matter what it is. If they're all the same, the gain will be -3. You got 3 resistors in the feedback path, gain is -3. Okay. A standard standard inverting amplifier, the gain is feedback resistor over the input resistor. So if you have a 3 kilo ohm resistor in the feedback loop, and you have a 1 kilo ohm resistor in the input loop on the input side, it's simply -3 over -1. Easy to do. Resistors are fine. What if you need a very high gain? Then you would have to use a very high value of resistors in the feedback path, right? Input, feedback. This RF would have to be very high. So if you wanted a gain in excess of 100, we'd have to use 100 kilo ohms in the feedback and then 1 kilo ohms in the input. That causes other kinds of problems. 100 kilo ohm resistance is very high. That means the current is going to be very low. So again, those will also affect on the functioning of the circuit. Okay. Theoretically, we would say that, yeah, it should work, but it will not. Okay. But by using this kind of configuration, if I use R1 and R3 as 1 kilo ohm, and I use R2 and R4 as 10 kilo ohms, standard resistors with lower value, my gain is in excess of 120. If I plugged in more resistors, if I did a circuit that looked like this, for example, we'd have even more higher gain. We'd have even better control over our output. So again, we can obtain a higher gain by simply configuring our resistors in the feedback path. Okay, you can obtain a higher gain. All right, any questions? Okay, so then let's move on. And there was problem 13.21 from the book that I was to do, but there was some sort of error in the solution. So I'm trying to resolve this. So I might either directly copy my annotations later, or I might create a small video, or I might do it on Monday. But I need to redo the solutions to this problem. Okay, so I'm not going to touch this for now. We are looking at active filters, and we looked at low pass filters with a capacitor in the feedback path. Let's look at high pass, where you have the capacitor in the input side. What kind of filter do we expect? High pass. States so on the slide. So this would be rather straightforward, because if you remember the passive filter configuration right here, I said at high frequencies, capacitor is a short circuit, so V out is 0. And at low frequencies, capacitor is open circuit, so V out is equal to V in. In reality, the same circuit is used as both a high pass and a low pass. If you take the output across the capacitor, it is a low pass filter. If you take the output across the resistor, it's a high pass filter. And so in the active filters, it functions the same way. You have a capacitor in there. As F tends towards infinity, capacitor is a short circuit. And so V in is passed through. As F tends towards 0, low frequency, capacitor behaves like an open circuit. V in is blocked. Therefore, this is a high pass filter. It allows high frequencies to pass through where low frequencies are blocked, hence a high pass filter. And again, depending on the ratio of R1 and R2, you can apply a certain gain to this filter circuit. Okay, so this is known as an active filter. Active filter. You can impart a certain gain to your signal. If you simply use passive components, which are used in crossover networks, so inside speaker boxes, those are passive components. They do not amplify the signal. Active filters like these will filter the signal as well as amplify it. So most of our circuits, electronic circuits nowadays, they all use active filters. And there's one more kind of filter we can obtain by combining these two signals together. So this right here is the low pass at the front end. This right here is a high pass. So low pass filter, high pass filter. AV is 1, AV is 1, and here AV, the gain is minus RF over Rin. Okay. So this is frequency V out. F V out. And at the output here, you'd obtain a band of frequencies that is allowed to pass through, hence a band pass filter. Anyone ever have a boombox with like manual sliders of graphic equalizers? That's what that circuit is. Each of those sliders in a graphic equalizer represents a band of frequencies that is allowed to pass through. So when you move the slider up or down, you're actually filtering out those frequency components. And when you move it up, you're applying some sort of amplification to those frequency components. And so nowadays, of course, everything's digital, done in software. But when they first came out with these hardware graphic equalizers, you'd slide it up or down. You're changing the gain of your amplifier signal. Okay. All right. Any questions? Okay. All right. So say we come to the end of chapter 3. That is the end of electronics, the end of our electronics journey. Now we are going to go into something completely different, and that is digital logic circuits. This is the fun stuff. This is what non-EE engineers love the most when we actually get to the lab, especially. All right, logic circuits. Logic circuits are basically the circuits that are used in digital applications nowadays. Okay, so so far we have studied continuous signals, analog signals. Analog signals can be of random shape, right? We have sine waves, triangular waves. Those are all had defined functions, but they all had continuous values. Okay. Digital signals, on the other hand, are discrete. They have a fixed value for certain points of time. Okay. So signals can be of multiple kinds. When we talk about signals, we can refer to like voltage or current. For digital signals, we refer that they are on or off. Okay, on or off. So digital signals have a fixed value with respect to time. They're also known as discrete time signals because they have discrete values. And these are continuous. Okay, continuous. So here's an analog signal, right? Standard analog signal. This could be the electrical signal captured by a microphone, let's say. And this is the same analog signal with noise added on. Okay. What happens when you have noise added on? If you ever try to use an AM or FM radio, passing between two transmitting stations, you might be able to pick up both transmitting stations at the same time. Those are analog signals that are being broadcast, right? So they are interfering with each other. The surrounding electrical signal that is not desired is noise. Okay, so here's the same signal with the noise, and so the value of the signal right there, and let's say at this point, is different, and so the resulting output would be different. In a digital signal, when you transmit, it's supposed to have a flat line, meaning the same value at certain points, right? So if you're transmitting from A to B, let's say, if you transmit this signal, digital signal, from A to B, point A to point B, it might pick up some noise along the way that is represented here. Okay. What happens then? Well, at the receiving end, it recognizes that the value is supposed to be fixed, and it rejects those noise signals. And so when we define noise as any unwanted signal in an analog system, it shows up and it's not rejected. In a digital system, noise rejection is built in. Okay. Noise rejection is built in. So that's one of the advantages of digital signal. So now we are working, and I said name of the chapter is logic circuits, right? So we say it's digital logic circuits. We are training our machines to perform digital calculations, okay, versus analog applications. So we have to learn the math, we have to learn the language so that we can talk to these machines or understand how these machines work. Okay, so we are going to learn about, I'll come back to the slide, the binary number system. Okay, because that is the only language that machines can understand. For machines, all the electronic circuits and the logic circuits are built upon a system being either off or on. Okay, there are only two states that it understands, either on or off. The light switch, for example, can either be on or off. However, if you build a dimmer in there, you can modulate the intensity of the light. So that's analog. Okay, but if it's simply on or off, that's a digital system. And so a graphical representation for that would be as shown here. This would be on and this would be off. So where a voltage is present, we term it on. Where a voltage is absent, we say it's off. Okay. So on and off are the terms that we use, but the system itself simply sees the presence of a voltage or absence of a voltage. Make sense? So there are only two values. Okay, two values. Hence, binary number system. How many of you are familiar with the binary number system? Some of you. So you probably get the joke. That is binary for 2. In decimal number system, 1 0 would be 2. And I just had this here because I liked it. This is again courtesy of Chuck Bland. In binary number system, he's actually right. All right. Putting back here. Okay. All right. So as I said, machine itself, when I say machine, let's say devices like transistors, diodes, they do not if you are designing a digital system, then they do not understand the concept of on or off. It's a concept we apply, right? They only see presence of a voltage or absence of a voltage. Okay. So when designing such systems, we define the levels. What consists or what is considered as presence and what is considered as absence. Okay. Presence being on, absence being off. So we could say if we have a system of, let's say, 5 volts, let's say 5-volt system, right? That's a 5-volt level. So between a particular time, if the voltage was 5 volts, you would say the system is on or the signal is on, right? However, what if there is some noise that is added on there? Either it exceeds or it drops below a certain level. Do we still want to consider it to be on? Right? Noise signal can be applied in any direction. It could either add on or it could subtract from your data. If it subtracts from your data, now your 5 volts could have dropped to like 4.3. So you design your system to accept that 4.3 volts, if that's what we want to do, right? So we design our system to accept 4.3 volts as being on. And that is called building a noise margin into our digital system. So, and that's noise margin is NM. And H stands for high, L stands for low. Again, the point is, if noise comes into our system and gets added on to our system, to our signals, we build in certain tolerance into our system so it still recognizes. If it drops in value, we might still want it to be accepted as on. And in cases where it's off, let's say something like this, where it's supposed to be off, if noise arrives and raises the level of our signal, meaning it goes up, increases, we might still want it to be off or considered off. So we build in noise margin tolerance for 0 also, which is here and here. Okay. So this is considered to be logic 0. This is considered to be logic 1. Absence is off or logic 0. Presence is 1 or logic 1 or on. Hence the binary number system, 0 and 1. We have to speak the language of the machines. And then this is the noise margin that is built in there. NML stands for the noise margin for the low level. NMH stands for the noise margin for the high level. So if a noise signal is added on to our logic 0 levels, up to this point, it would still be considered as logic 0. The same thing when it's logic high. Okay. Because if it becomes undefined, then the system would not work. And this is how a digital system is better at rejecting noise signals. Okay. So the binary number system. Oh, any questions thus far? Let's take a pause. So far, so good. Okay. So binary number system basically works with powers of 2. Decimal system, of course, we are familiar with, works in powers of 10. Decimal number system, we go from 0 to 9. right? 0 to 9. Binary number system, we go 0 to 1. That's it. And then there's hexadecimal. Hexadecimal goes up to 16. That goes from 0 to 9. And then for some reason, not some reason, they used alphabets A, B, C, D, E, F. That goes from 0 to F. Standard rules apply. We have the least significant bit, which is at the rightmost bit, and the most significant bit, so going towards the left, LSB and MSB. Okay. Each bit is 1 point of data, okay, or 1 line of data. It can store 1 piece of data, okay? And so bit is represented with a lowercase b and is 1 unit of data. 1 unit of data. 8 bits together is 1 byte. And byte is represented with uppercase B. Uppercase B. So the first microprocessors were 4 bits, then 8 bits, then 16 bits, and then we had 32 bits. And now, of course, we use 64 bits. 64 bits, with each increasing number, the amount of storage, the amount of memory, the amount of processing doubles. Well, actually not doubles. It's 2 raised to n, multiplies. So if you have 1 bit, you can only store 2 bits of it, like either 0 or 1. If you have 2, you can store 4. If it's 3, you can store 8, and so on and so forth. So if you have 64, that's a very large number. All right, binary number system. How does it work? Well, we always start from the left, go towards the right. Okay. So let's take this number, 1101. So 1101, start with 10 raised to 0, 10 raised to 1, 10 raised to 2, and 10 raised to 3. Okay. So 1101 would be 1 into 10 raised to 0 plus 0 into 10 raised to 1. So 1 into 10 raised to 2, and 1 into 10 raised to 3 gives us 1,000 plus 100 plus 0 plus 1. That's how we arrive at 1101. And the decimal side, 0.01 0.11 would require 10 raised to minus 1, 10 raised to minus 2, and so on and so forth. And so you get 0.1 and 0.01 so on towards the right, and here towards the left. Now, because it's a binary number system, the base is 2. So if you were to convert this, we would use, this is, let's see, right here. Okay, 1101, and this is 0.11. So to convert to decimal, 1 into 2 raised to 0, 0 into 2 raised to 1, 1 into 2 raised to 2, 1 into 2 raised to 3. gives us 8, 4, 0, and 1. 13. And on the other side, it's 2 raised to minus 1, 1 into 2 raised to minus 2 gives us 0.5 and 0.25. And we end up with 0.75. And that's how you would convert decimal to binary. I'm sorry, binary to decimal. Binary to decimal. Okay, and this is the binary value. The table itself is rather straightforward. If we have our decimal number table, what do? We start with 0, right? We go 0, 0, 0, 0, then we add 1. So we got 0, 1, and then we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 0, 0, 1, 0, 0, 2, 0, 0, 3, 4, so on and so forth until we get to 0, 0, 9. After 9, we go back to 0. So this 9 changes to 0, and then the second most significant bit from the left changes to 1. So this 0 stays the same. So we got 0, 1, 0, 0, 1, 1, 0, 1, 2, and so on and so forth until we get 0, 1, 9. After we reach the limit, 9 changes to 0, 1 changes to 2. And thus, we have the decimal number system. 1, 2, 3, 4, 5, 6, 20, 30, 40, 50, all the way to 90, right? Binary is the same. Here, we only have 2 options. We start with a 0 first. Next step is 1. So we get 0 and 1. We exhausted our bits in the first 2 steps. Then this 0 changes to 1, 1. And then this repeats. Okay. So we obtain for decimal 0, binary would be 0, 0, 0, 0. Decimal 1 would be 0, 0, 0, 1. Decimal 2 be 0, 0, 1, 0. 3 would be 0, 0, 1, 1. And that's only if I'm taking 4 digits, right? If I have 2 bits, I can only go up to 2. So 0, 1, 2, 3 is 0, 0, 0, 1, 1, 0, and 1, 1. Once you exhaust that, you go to 4, 1, 0, 0, and you start all over again. Okay, so it keeps repeating. The least significant bit will keep going 0, 1, 0, 1, 0, 1, 0, 1. In decimal, we go 0 through 9, then it repeats 0 through 9. In binary, it's just 0 and 1. So the least significant bit always goes 0, 1, 0, 1, 0, 1, 0, 1. You move 1 spot over to the left, and it goes 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. You move to the third significant bit, it goes 0, 0, 0, 0, which is right here, and then 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and so on and so forth until we exhaust all options. But we have gone over 1 p.m., so we'll end class here today. Review all of the work that we have done this week. It's a Monday quiz based on Monday, Wednesday, Friday. Okay. The next homework due date is not until the end of February, so that will be brought forward. Okay, so keep an eye out for that. And when I bring it forward, meaning the due date will be set for the next few days. I will post an announcement. Friday quiz today, do not forget. As always, if you have any questions, reach out to me, email, and I'll be available.